Okay. Hello everyone. Welcome to IBS BIMAC Colloquium. This is a last talk of this semester. Today we have Professor Hiroya Nakao as today's colloquium speaker. Professor Nakao earned his PhD in physics from Kyoto University in 1999. And by following this doctoral study, he held a postdoc position in University of Tokyo and RIKEN. And he then served as an assistant professor in the Department of Physics at Kyoto University. And then in 2011, he joined the Tokyo Institute of Technology, where he is currently a professor in the Department of Systems and Control Engineering. He is internationally recognized for his pioneering work in nonlinear dynamics, synchronization, self-organization, and stochastic process. His research integrate mathematical rigor with the application to complex systems like spanning physics, biology, and engineering. Please join me in welcoming Professor Hiroya Nakao.
Okay.
Mhm.
Thank you very much for the great introduction. Okay. Yes. Can I start?
Yeah, please go ahead.
Okay. Okay. So, good. Hi. Nice to meet you. I'm Hiroya Nakao from Institute of Science Tokyo, which was formerly in Tokyo Institute of Technology. So we merged with another university and changed the name. Okay, so today I'd like to talk about Koopman operator approach to complex rhythmic systems, and not too much high detail, but more like broad and general introduction. Okay,
Mhm.
so let me start. So, and I guess many of you already familiar with the topic. So maybe I can. Okay, the first 10 minutes will be quite introductory. Then I go into the a bit more detailed topics. So okay, so this slide shows what I have been studying for in my career. So basically, I am a physicist. I started in physics using dynamical systems theory or stochastic processes for various systems. And these are some of the systems that I have briefly touched on, I would say. So they are very different systems like physical chemistry, fluid mechanics. But one thing in common is that they are self-oscillatory, so they are oscillating. So basically, they are all oscillators. That's why we can kind of use similar methods for analyzing these systems. Okay, let me very briefly go through the introductory part on nonlinear rhythms and synchronization. So as you know very well, so there are various nonlinear rhythms in the world, like metronomes, fluid oscillations, animals, gates, or circadian clocks. And those systems are typically modeled as dynamical systems. Or maybe we can also add some noise, but typically we use nonlinear dynamics to describe them. So it's like this. I think I can skip this slide.
Mhm.
And in-cycle oscillators are stable self. Okay, so we have stable self-sustained oscillations in diverse real-world systems in every disciplines: physics, chemistry, electronics, mechanical, biological systems. And here we can have such stable limit cycles where we need energy input, dissipation, and nonlinearity. And we call limit cycle oscillator the dynamical system with a stable limit cycle. Okay? And one typical example is the Fitzhugh-Nagumo model. There are many examples. Okay, I guess many of you know this model. So they are invented by Fitzhugh, then experimentally implemented by Nagumo a long time ago. And this is Nagumo's circuit. So he used this, he connected these circuits to simulate the propagation spikes in this circuit.
So they work independently, not together.
No, they are independent. So
Ah,
I guess, as
yeah.
far as I know, they are independent.
Oh, I see.
Yeah, so I guess Nagumo saw Fitzhugh's paper, then immediately
Uh-huh.
implemented it experimentally.
Oh, wow.
Okay, I'm not so sure if
But anyway, wow, it's very interesting. I thought that Nagumo also theorist, but he did some experiment as well. Wow.
he, yeah, he's an electrical engineer, and he
Hmm.
did both kind of, yes.
Wow.
Okay, and we can still see this circuit
Oh.
if we go to University of Tokyo Museum.
Oh. Okay. Oh, next time definitely.
Okay, great. So I guess you already know these pictures. So if you couple limit cycle oscillators or self-sustained like metronomes, they synchronize. And this was already found by Christian Huygens, which I never pronounce correctly. And okay, and I guess many of you know these very famous experiments. So interacting self-sustained oscillators can synchronize. And I was wondering where this video came from, and it's from Lancaster. I found it out from Lancaster University. This has been already nearly 20 years on YouTube. Okay, and then there are many natural systems like flashing fireflies that synchronize, or even people on the bridge can synchronize. I guess you
But
know
as the people
this.
poured over the bridge,
Very well.
it was clear something was wrong.
So even people can synchronize with each other because they are like metronomes on a plate. So synchronization is a very quite a general property of nonlinear oscillators. And this is another example of the Belousov-Jabotinsky reaction from Kitahata-san, Chiba. So, okay, this is a self-sustained oscillations with the pH of the liquid. And if we put them on a sheet of coffee filter, then at each point we have oscillations, so they propagate and diffuse, and eventually we typically have spirals like this. And this is millimeter to centimeter order, but we can observe exactly the same pattern on a platinum surface where CO and CO2 are oxides and deoxides oscillating. So this is like micron to nanometer orders. So we can, this type of patterns are quite universal in oscillatory systems. And we can also find them in slime molds and even on a heart. And if this happens, we are in trouble. So we have to use AED to reset it. Okay, and also, of course, gaits of animals are oscillations. So they are controlled by synchronized oscillation of the legs. And it is considered that there is an area in the brain called central pattern generator, which generates those synchronized rhythms to control the animal gaits. And there are also robots based on it. Okay. So we have a lot of synchronization in the real world. And okay, so we want to analyze them mathematically. And okay, so the limit cycle oscillator is at least two-dimensional, and it is of course nonlinear. So as you know very well, we cannot solve the equations for nonlinear oscillators in general. So we know that they are oscillating, but we cannot analytically express it. But so we need to consider something, some approximate method. And one such method, which is very classic, like from Winfrey 50 years ago, is the phase reduction. So, okay, because we are considering rhythmic systems, so the most essential dynamics is described by just a single phase equation. So what is the most important characteristics of this dynamics is the phase rotates periodically. So then, as I will explain you, there is a method so-called phase reduction, which simplifies this multidimensional equation with external forcing to this phase equation. So we can reduce from any dimension to one dimension with simpler form. Then, even if we have many such oscillators, we can still have some simpler phase model. Such a method has been developed by these guys for a long time. Okay, and this is a very, this is, I guess, I guess this is too simple for you, but okay. First, we can, what we typically do is first we introduce the phase along the periodic orbit in such a way that the phase always increases with a constant omega frequency. Then, even if the original signal is like this, nonlinear, we get this simple dynamics for the phase increasing from 0 to 2 pi periodically. And later I will introduce this in a more general setting. But then we have, okay, for now we have this very simple oscillator model, just this equation, which can immediately be solved, and this corresponds to the dynamics on a limit cycle. Okay. So if we know the phase, we can reconstruct the state on the limit cycle. Then the z function comes in. So of course, we are not only interested in a single oscillator, but we typically are interested in coupled oscillators. So we have to consider the effect of other oscillators or other external inputs. And this is, in the simplest manner, this is incorporated like this equation. So we introduce a z function, which we call phase sensitivity function, or which is also called phase infinitesimal PRC. And it's like this. So we give a pulse to the oscillator, then the phase shifts, and this is measured, and we can get this z function. And it has been experimentally measured in many systems. Like, and this is interesting. So this is our own result on some simple electric circuit, and this is for human circadian rhythms. This is a blood melatonin level, which oscillates with 24 hours period. And then these authors gave light stimulus, very strong light stimulus to see how it advances or delays the circadian rhythm. And they got this curve. So this is a very typical phase resetting curve. And okay, from this PRC, we can get the z function if the stimulus is not too strong. Okay, and this can be used to write down this equation for the analysis. And this shows just two coupled oscillators synchronizing. And they are just attractive, so they eventually synchronize. I think I can skip it. Yeah. So, and such dynamics can be modeled in the simplest manner by two coupled phase oscillators. And here, okay, we have two phases, theta 1 and theta 2. And in here, we assume the simplest sinusoidal coupling. Then, if we look at the phase difference, we get this one-dimensional equation, which can easily be analyzed. And depending on the frequency mismatch and coupling intensity, we have synchronization or continuous drifting. So this desynchronization. And this synchronization region is called anode turn. Yeah. So this is a very simple phase model. And okay, so this is, I guess this is very well-known video. So it's from circadian rhythm of SN neurons. There are many neurons getting activated or inactivated with 24 hours period. And if you, so such a model may be modeled as oscillators coupling through some interaction network. And the simplest of such model is a so-called Kuramoto model, the globally coupled phase oscillators. And here we have 400 oscillators, and this is the slowest one. These are the fastest one. And if we start simulation, they become synchronized. So these are too slow to be synchronized. These are too fast. But others, okay, here this dominant part becomes synchronized and start to oscillate with the same frequency. So this is so-called corrective synchronization transition. And this was found by Kuramoto 50 years ago by using such phase model, and above some critical coupling intensity, the oscillators synchronize and start to exhibit macroscopic oscillation. And he just got Koopman medal for this year. And this I wanted to show. So this is such one application of the phase model. So we can, for example, design a central pattern generator for 6-legged robots. And here, a 6-legged robot is mimicking insects. And it's like, so, and maybe you know, insects have 3 or 4 or even more gait patterns. So the order of the movement of the legs are different depending on their speed. So this Namura was interested in how this can switch different gait patterns. So he invented a network to control the legs like this. And because he is an engineer, he could also make a robot like this. So at this point, we have no application of this robot, but at least we could mimic some insects using phase model. Okay. Then so this is okay. Oh, I already used 15 minutes. Sorry. So this is the introductory part. Then now I move on to a bit more mathematical part. Okay. So basically, we are interested in dimensionally reduction of dynamical systems. And our world is typically dissipative. So we have friction. So we are not in a Hamiltonian world. We are in a dissipative world. So the state of the system is very typically attractive to low-dimensional attractors or manifold in the phase space. And so even if we have very high-dimensional system, the essential dimensionality is quite low. Okay, so for example, in these fluid systems, the fluid equation is of course infinite dimensional. But if we are interested only in this Kalman vortex streets, it's just oscillation. So we need only a single phase barrier to describe this. So the phase reduction that I mentioned is one of such very typical dimensionality reduction method for an oscillator. So basically, we can reduce this high-dimensional system to a single-phase equation like this. Okay. And of course, the phase reduction theory has a long history by its own. But recently, the so-called Koopman operator approach became quite fashionable. And Koopman operator is also quite old. It's like 100 years old. But they somehow recently, mainly due to Igor Mezic at UC Santa Barbara, he popularized it. Then we got into the study, and then we got new insights. So I would like to talk a bit about it today. Okay, but let me start from a very elementary operator. So suppose you have a very simple two-dimensional system. So here, this equation, U and lambda are negative parameters. And of course, we can see that origin is a stable fixed point, and the Jacobian matrix is given by this. And for this system, the infinitesimal Koopman operator, or generator of the Koopman operator, is defined like this A.
Mm-hmm.
And you can immediately see that this A has some eigenfunctions given by this phi mu and phi lambda. And mu and lambda are the eigenvalues. Okay. And you can just plug this x here, and you get mu x, and similarly for this phi lambda.
Mm-hmm.
Then, okay, the next step is quite important. We consider these two eigenfunctions, which are called principal Koopman eigenfunctions of this system, as the new coordinates. So from x and y, we move on to phi mu and phi lambda as new coordinates. Then we can easily see that the system is linearized. So the original system is nonlinear, but by introducing these nonlinear transformation defined by the Koopman eigenfunction, the system is linearized. So we can deform this original nonlinear system into this very linear, simple system. Okay, and this example is, I guess, taken from this famous guy's paper. And okay, so in the new variables, the system is globally linearized. It's not a linearization near the origin, but it's a global linearization. Okay, now, as the next step, suppose one of the eigenvalues is very negative, right? Lambda is very small. Then we see that this second equation quickly relaxes to zero. So we can, as a crude approximation, we can eliminate this equation by assuming phi lambda is simply zero. Then we end up with a single equation for phi mu, and which is one dimension. So what we have done is to globally linearize the system, then eliminate one dimension to get a reduced equation. So the Koopman operator analysis can, how to say, give a systematic method to globally linearize and reduce the dimensionality like this. So, and I would say this is exactly what is done in phase reduction. Okay, and we can also introduce, relate the important notions like inertial manifold to the Koopman eigenfunction. Okay. Now, okay, then let us be a bit more general. So, okay, I guess you know already something about the Koopman generator, but okay, so suppose we have a dynamical system, and the flow of this dynamical system, which maps the point x at time t to point at x time t plus tau, is s. We use s tau for it. Then, okay, so this is an ordinary evolution of the system state. Then we introduce an observation function which maps this system state x to some complex variable. This should be actually complex. Okay, then the Koopman operator u tau is defined by this equation. Okay, and this equation should be read like this. So typically okay, suppose x is the initial condition, then the state at time tau is s tau x, and we observe this s tau x by some x observation function like our gauge or measurement gauge. Okay, but on the left hand side, it's like this. So instead of evolving the system state itself, we keep the system state as original state x, but rather evolve our measurement gauge, the measurement function, okay, in such a way that they give the same results. Okay, so this is the definition of the Koopman operator. So the Koopman operator maps the observation function to a new observation function. Okay, then the generator of the Koopman operator, it can be, okay, for small tau, we can get this equation. And this is so-called d derivative of this system. Okay, and this is actually quite old. But originally, Koopman introduced this only for Hamiltonian system, inspired by quantum physics. Then von Neumann made it very rigorous in the next year. But only recently, this has started to be used for dissipative systems, and that was big hit for applied mathematics and control theory. Okay, so it's like this. So generally, we consider the system state evolves with time and observe it with the same observation function. But in the Koopman viewpoint, we keep the system state, but rather evolve the observation function from f0 to ft to f2 tau by the Koopman operator in such a way that we get the same observation value. Okay. And of course, we introduced, original system was finite dimensional, but the observation function is in infinite dimensional space. It's of course complication, but then we can get the linear operator. So it depends on what we want to do, but this may give some new insight. And because this Koopman generator A or Koopman operator is linear operator, we are tempted to consider the eigenvalues and eigenfunctions. And they are actually very important. And because there can be infinitely many Koopman eigenvalues, but there are important Koopman eigenvalues and eigenfunctions in particular for fixed point or limit cycle, for hyperbolic attractors, and for fixed point for limit cycle, we have this Jacobian and or the maybe Floquet multipliers, and they are typically characterize the linear stability, but those linear stability exponents are included in these Koopman eigenvalues. Okay, and they are called principal Koopman eigenvalues by Mejic. And okay, I'll come back to this point later. Okay, but anyway, if these eigenfunctions span a complete basis, we can expand some function using these Koopman eigenfunctions. And then if we can expand the observation function by using those eigenfunctions, we can we can know the future state just by applying the Koopman operator to this f. And it's because it's just a linear operator, we can get this linear prediction, linear evolution. We can know the future state by this linear evolution. Okay, and of course, mathematically, it's quite difficult to, I guess, show the completeness of the Koopman eigenfunctions, and they can also have continuous spectrum, which are quite difficult. I cannot go into them, but if we can assume this, it's clear we can get this future equation for the future prediction. Okay, and this is okay. So this slide shows if we have two Koopman eigenfunctions, then their multiplication is also a Koopman eigenfunction. Okay, or so we basically have infinitely many Koopman eigenfunctions, but as I said in a previous slide, for linearly stable fixed points or limit cycles, the Koopman eigenvalues include the eigenvalues of the Jacobian or the Floquet exponents for the case of limit cycles, which are, so we have n such exponents. Then there is an important fact that analytic observables, so that can be Taylor expanded, can be represented only by using these principal Koopman eigenfunctions. So there are infinitely many Koopman eigenfunctions, and we need all of them to expand F. But if we are interested in a basin of some hyperbolic fixed point or limit cycles, we can use this expansion. So we only need n eigenfunctions. And we can again evolve this f by applying this ut to this. So this is actually important, and you can find some proofs in this Mauro Nejic paper. Okay. Okay. So summarizing, so we have a system, nonlinear system, and we now focus on the system is some exponentially stable fixed point or limit cycle. Okay. And so, okay, this is a system. And then we have some fixed point or stable limit cycle whose stability exponents are given by these lambda 1 to lambda n. Then we can introduce the associated principal Koopman eigenfunctions psi 1 through psi n. Then what we done in our first example is we used these Koopman eigenfunctions as the new coordinates, which is represented by yi here. And in this new coordinates, yi, system is globally linearized. And this is quite easily shown in this one line. So if we can find such Koopman eigenfunctions, we can immediately show it evolves linearly with time. Okay. And moreover, if many of these lambda i's are very negative, then we can eliminate those y to 0. Then we can reduce the dimensionality. So we can systematically linearize, then reduce the dimensionality from the Koopman operator viewpoint. Okay. So this is just a kind of a general theory. Of course, in practice, we cannot solve these Koopman eigenfunctions. So this is a kind of idea, but okay. So people typically like explain like this. So we have a finite dimensional nonlinear system, but we lift it to a high dimensional space of the Koopman eigenfunctions. Then the dynamics becomes linear, but it's infinite dimensional. So there is of course a trade-off. But maybe in some cases this linearity helps a lot the analysis. Okay.
So, Hiroya, so in your first example, two-dimension becomes two-dimension in your first example.
Yes.
But in real life, it can be much higher dimension.
Yeah. So yes. So okay. So this is a general theory. So suppose x is n-dimensional. So we have n exponents.
Okay.
But if n minus one of them are quite negative, like minus 100, we can eliminate them. So we end up with just a single dimension, even in such a case.
Gotcha.
I will show this for the limit cycle example.
Sure. Okay, that's good. Thank you.
Okay. Then, of course, we are interested in some perturbations. So we are this is the original system, and this plus p is a small perturbation. Then we want to simplify this system. So we introduce the Koopman eigenfunctions and use them as a new coordinates, yi. Then the equation for this yi is like this, so you can see it. So we have this linear part plus vi function multiplied by the perturbation. So we get some response function or sensitivity function. Okay. And this sensitivity function is given by the gradient of the Koopman eigenfunction. And if we, for example, eliminate the fast decaying variables from n plus 1 through n, then we get a lower dimensional, m-dimensional reduced linearized equation in this form. So this is a kind of a general theory for weakly perturbed dimensionality reduction of weakly perturbed nonlinear system by using Koopman eigenfunctions. And this I will show this is exactly the phase reduction in a classical sense. Okay, so this I think I'm using up time, so let me go on quickly. So then we move on to the phase reduction, which was originally developed from a geometrical viewpoint, but then the Koopman operator theory gave us some new idea and generalization. Okay, so this is a definition of the phase. So I think I can already skip it. So we can introduce a phase on a limit cycle, which increases with a constant frequency. Then traditionally, the next step we do is introducing the asymptotic phase in the basin of this limit cycle. So we introduce an asymptotic phase function, theta, which maps the system state to a phase value, satisfying this equation. So this is just theta dot equals omega in the whole domain of basin. And such a function is called asymptotic phase function. And the level sets of asymptotic phase functions are the isochrons. I guess you know the idea very well. So it's like these blue curves. And if you start on any point on this blue curve, you eventually relaxes to the same point on the limit side. Okay. And if we can introduce such a phase function, then introducing the phase of this oscillator as this lowercase theta, then it obeys this equation. So this is a classical phase reduction. Yes. Okay. And we can also introduce another function, which we call amplitude, a bit misleading, but we call it amplitude. So it's a function R of x, which maps the oscillator state to a complex value in such a way that this equation holds. So R dot is mu R. And so we all know that the system state eventually relaxes back onto the limit cycle. So by introducing some coordinate transformation, we can represent this relaxation to the limit cycle by this equation. And such a function, coordinate transformation, is called amplitude function. And okay, and this is actually Koopman eigenfunction itself of this limit cycle. And such a function has been used already in old literature, but the Koopman operator made it quite clear as an eigenfunction of the Koopman operator. Okay. And now, so this is a relation between the Koopman eigenfunction and those phase and amplitude introduced rather geometrically. So this is a limit cycle. We have a periodic solution, and we can consider the principal eigenfunctions of this limit cycle. In here, these are the eigenvalues. So we have one eigenvalue, I omega. This is generally taken as 0, but we can also take it as I omega. And we have a pure imaginary eigenvalue corresponding to the phase. And then we have eigenvalues with negative real parts, which correspond to the relaxation modes toward the limit cycle. So the spectrum of, I don't know what it is. Okay, sorry. The spectrum of the Koopman operator for limit cycle is like this. So for this very simple Van der Waals, we have just 2 dimensions. So we have 2 principal Koopman eigenvalues, omega and mu, and they are like, we have omega, I omega, and mu here. Then we have a lot of more Koopman eigenvalues. They are just combinations of this I omega and mu. Okay, so these are the principal eigenvalues, and the associated eigenfunctions the principal eigenfunctions satisfying this equation. Okay, so we focus only on these two values. Then sorry, this is a bit bad. Sorry.
It's okay, no problem.
Sorry. Okay, so let us recall that the Koopman generator for this system is just given by this f dot nabla, and our definition of the asymptotic phase is such that the theta function satisfies this equation. Okay. Then, if we consider the complex exponential psi of this theta, so exponential I theta, then we can show that this is actually a Koopman eigenfunction, this eigenvalue I omega, because this equation is satisfied. A psi is I omega psi is satisfied. So this is exactly the Koopman eigenvalue equation, and this psi is a Koopman eigenfunction. So the traditional idea of asymptotic phase is exactly the correspond to the Koopman eigenfunction. And similarly, the amplitude that I defined is nothing but the Koopman eigenfunction for the second Fourier exponent mu here, satisfying this equation. Okay. So those phase and amplitude functions have been somehow geometrically introduced in the past literature, but they are exactly the Koopman eigenfunctions of the limit cycle. So in this sense, the Koopman operator theory gave us some new insights into the phase amplitude. Then, as I already explained, suppose we have some small perturbation, then we introduce the phase and amplitudes like this. Then, at the first order approximation, we have this theta equation for the phase. So this is a traditional phase equation. And we can also get this amplitude equation. And this z function is a gradient of theta. So this is a phase sensitivity function. And this I function is a gradient of R. And this was only recently introduced, and this is called isostable response function. We call it amplitude sensitivity function. Yes. So what we do is introducing a nonlinear transformation to the limit cycles and kind of linearizing it, and then introducing the perturbations at the first order like this. Okay. Sorry for the mess in the slides. I'm sorry. Okay, and maybe I should skip some of the slides, but if we are interested only in small perturbations, we cannot calculate the Koopman eigenfunction analytically, of course, but we can calculate this z function or I function, the phase sensitivity or amplitude sensitivity, by solving the so-called adjoint equation for this system, given by this for the z and this for I. And this is much easier, and we can just numerically solve z and I, then use it for the phase and amplitude equations. Okay. So this is a summary. So for limit cycles, weakly perturbed, we can introduce the phase and amplitude as Koopman functions. And as a first order perturbation, we get this phase equation and amplitude equation. So we are deforming the original nonlinear limit cycle to such a simple object and incorporating the perturbation as a first order. Okay. I think I have 5 minutes left, so okay, let me skip some of the slides. So there are some applications of these phase and amplitude equations, like optimization. But let me skip. Sorry. So we can use like the amplitude equation to suppress the deviations from the limit cycle. Sorry, I skipped this.
Mhm.
Then we can generalize the theory, for example, to networked dynamical systems, which is just a big limit cycle. So it's kind of an obvious generalization. And even for such networks, for example, this is a network showing collective oscillations. But as long as this network is a limit cycle, big limit cycle, we can do the same. So we can reduce the dimensionality to 2 in this case. The simplest is 1 for the phase. And if we are also interested in the amplitude, we can introduce amplitude. And this is the equation, phase amplitude equation for such a system. Then we can use this phase equation for synchronization analysis and the amplitude equation for like controlling the system or evaluating the deviation from the limit cycle. Okay. This is just synchronizing networks. Not so interesting. Yeah, so just synchronizing networks, and we can analyze this synchronization using such phase equations. Okay. Then I already showed these pictures. So we have spatial temporal patterns that shows limit cycle oscillations. So they are, of course, very high dimensional, but still they are limit cycles.
Mhm.
So if we introduce the Koopman eigenfunctions for these systems, we can reduce the dimensionality as in exactly the same manner as before.
Mhm.
Such examples are like spirals of reaction diffusion systems or like those oscillations in fluids. And I'm sorry, so this is a bit too complicated. But we can formally generalize the Koopman operator theory to, in this case, to reaction diffusion system. So we consider the observation functional, then introduce the Koopman operator as a mapping from the observation functional to observation functional in exactly the same manner as before. Then for limit cycling systems, in this case, the reaction diffusion system, we again have pure imaginary eigenvalue, which corresponds to the phase, and at least one, actually many exponents with negative real parts. And if we focus only on the first phase mode and the slowest amplitude mode, we can reduce the dynamics of this reaction diffusion system to a set of phase and amplitude equations. I'm sorry, I have to skip the details, but by using the Koopman eigenfunctions of this reaction diffusion system. And so then if we have additional perturbation to the reaction diffusion system, okay, this is a very complicated system, but if we are interested only in the phase and amplitude, we can get the phase equation and amplitude equation in this simple form. So of course we have infinitely many eigenvalues, but we are focused only on the I omega and the slowest decaying mode. And such a description can still be useful depending on the situation. Okay, so we can do exactly the same machinery for ODE to PDEs. Of course, mathematically, to rigorously prove this is, I cannot do it, but should be very difficult. But at least formally, we can do this such a reduction, and it actually works. Okay, so let's consider a Fitch-Nagumo model with, okay, sorry, this doesn't move. So we have like targets, spirals, this moves. And here we are coupling two such spirals. So we consider two spirals and somehow couple them. there are actually such experiments using video camera and easy reaction. And you see they synchronize, and this dynamics can be analyzed by using the phase model, by the phase reduction. And it's like, not going into the details, but we can derive the phase equations from these spirals by introducing the phase and calculating the phase sensitivity functions. Then we can calculate how the phase coupling function and see how they synchronize or desynchronize. And in this case, we can have in-phase synchrony or anti-phase synchrony. Then this is kind of Kuramoto model of spirals. So we consider 16 spirals globally coupled, and I guess it should, yeah. Okay, so and this is a final state, and you see something here. Maybe somebody noticed it. So we have two cluster states of the spirals. So half of them are synchronized like this, and half of them are synchronized like this. And this is our initial state of the angles. Okay. So, and this can also be analyzed by using the phase model, by approximating the sensitivity function and calculating the phase model. Okay. So these are simple examples. Then, can I use 3-4 minutes more?
It's totally fine. Please go ahead. Yes.
Okay. Then let me finally briefly touch on data-driven analysis. Okay. So, of course, from the models, we can somehow introduce the z function and I function, which are the gradients of the Koopman eigenfunctions, or more explicitly, the phase function or the amplitude functions. But what happens if we do not know the mathematical model? And such a situation is, of course, in modern world, quite important because we have more and more complex systems, and we don't have the exact mathematical model, but we still have much data. So of course, the natural idea is to learn the system dynamics from data. So that's data-driven approach. So, okay, this is a noise fit Funagumo, and can we, for example, evaluate the phase and amplitude function from this data? And there are several methods to do this, and many people are actually focusing on it. And in particular, recently, in relation to the Koopman eigenfunctions, the so-called dynamic model decomposition is quite a major topic. There are thousands of papers already. Okay. So, and we are interested in getting the phase and amplitude equations from data, and so we want to learn the theta function and R function from data. Okay. And of course, this omega and lambda, but these are relatively easy. Okay. And okay, this is a first method that we tried. It's such a simple-minded idea. So we guess omega. Omega is quite easy. We just measure the period. Then we can also measure the Lyapunov exponent, which corresponds to the Floch exponent. And then using these mu and lambda, and we can use polynomial regression to fit the data. And it actually works. And okay, these are the fit Stewart-Land and Van der Poel, and we can reproduce the phase and amplitude function to some extent by using such idea. But this method requires so many data points, and I guess it's experimentally not easy. Okay, then we used another idea like machine learning. Here we are focusing on big data, but for now it's only for small data. So we use autoencoder to reduce the dimensionality of a system, and then it reproduces the original pattern because it's an autoencoder. And in this system, we require these latent variables to obey the phase and amplitude equation. So this is a kind of physics informed neural network. So we want to introduce some physics principle into the learning process. So here we require that these latent variables are literally the phase and amplitude, or I would say Koopman eigenfunctions, and evolve according to the Koopman linear evolution.
Oh.
Okay, so and such an idea had already been in this well-known paper. But it's more on Koopman, so we modified it for phase and amplitude. Then these are the results. So yeah, we can also learn the phase and amplitude functions, and also their sensitivity functions, Z and I, like this. And we need less data in this case. Then, and this is a third version we only recently published. This was done by Yamamoto-san, Kobayashi-san, and here we used Gaussian process regression. And so we want to minimize the usage of data because experimentally we may not be able to get such many data points. So this is a kind of regression, so we need less data and we can reproduce again the phase and here only phase functions. Okay, and compared to the polynomial regression, it's much better. Okay, and then the last topic is the dynamic mode decomposition, and I guess many of you know it. It's a well-known method for learning Koopman eigenvalues and eigenfunctions from data. And as I said before, the Koopman eigenvalues and eigenfunctions correspond to phase and amplitude functions for the limit cycles. So we can, in principle, we can use this. And I skip the algorithms as it's very well known. You can look into this paper, but it's quite easy. And we tried it. And in this case, for stochastic oscillators rather than deterministic oscillators. And I guess you attended a talk by Professor Lindner, who studied noisy oscillators. And I guess he mentioned something about Koopman or the asymptotic phase for stochastic oscillators. So here we are doing the same thing. So we consider noisy oscillator and estimating its noisy Koopman eigenfunctions. And they are slightly different from deterministic eigenfunctions. And we can, this is quite weak noise, but we can somehow reproduce the eigenfunctions, and they match with the eigenfunctions obtained from the original model from the adjoint Fokker-Planck operator. Okay, and we are kind of a bit competing in this topic, but of course I should mention that Professor Thomas and Lindner are much earlier. So they started already in 2014 by using the backward Kolmogorov equation to define the asymptotic phase for noisy oscillators. And only recently we noticed that it's just the Koopman. Then I guess they also noticed it. So kind of, yeah, but I respect them in that they first very seriously considered the asymptotic phase for noisy oscillators already 10 years ago. Okay. Okay, and this is the last slide. Sorry for taking too much time, but this is not my own study, but I just participated. And this was done by Fukami and Tyler from UC Los Angeles, and they are studying fluid mechanics, and this is a wing, and this is a vorticity field, and in their airplane simulation, the flow here is weakly oscillating, and so that in a stable condition. And then they introduce some big vortex here to hit the wing, then of course the fluid flow here is disturbed and the airplane becomes unstable. So their purpose is to destabilize this flow as fast as possible by some control. And of course, this is a very high dimensional system, so we cannot simply control them. But what they did is introduce the autoencoder to reduce the dimensionality of this fluid system. And then what they found is in this three-dimensional latent space, they found limit cycles. Then we can use phase amplitude. So they learned the dynamics by using the so-called Cindy and the polynomial regression, and then solved the adjoint equations to get the sensitivity functions, and then used those sensitivity functions to control these limit cycles in such a way that the deviated trajectory comes back to the original limit cycle as fast as quickly. Then they somehow succeeded in suppressing the effect of such a huge perturbation given to the flow. Okay, so this is a quite a very nice data-driven phase reduction analysis and control. So I like this study, though I only just commented on this part of this study. Okay, so this is a summary. So sorry for taking too much time, but I spoke about phase reduction and phase amplitude reduction, then the relation to the Koopman operator, and then showed that we can also do it in a data-driven manner. Okay, thank you very much for your kind attention.
Okay, great. Thanks so much. So we have enough time for the Q&A. Please go ahead. Please feel free to unmute and ask a question to the Professor Nakao.
Oh, just call me Hiroya.
Yeah, okay. Young, yeah, go ahead.
Thank you for the lecture. Actually, last week I asked Professor Benjamin Lindner
Oh, yes.
about the data-driven approach to his definition of phases. And actually, he also said that you can, but you need a lot of data.
Yeah.
Yes.
Actually, my question is about your paper on phase autoencoder. Actually,
yes.
Actually, I read it.
Oh,
and so I wondered, in your method, if the oscillation is not perfectly on the limit cycle,
sorry.
then if the oscillator is not on the limit cycle, if there is some deviation,
yeah,
I think it is a bit difficult to apply. What do you think?
Actually, we need time series outside of the limit cycle. If they are always on the limit cycle, we cannot learn it. So we need all these transient trajectories because we need the structures not only on the limit cycle but outside of the limit cycle. So okay, and sorry, I don't show the number of data points here, but for this autoencoder, the data necessary for the learning was much less than the polynomial regression. So the polynomial regression is really bad. Yeah, but of course this is a neural network, so it has too much power of learning. So sometimes it learns quite strange stuff. So yeah, it depends. I guess for this purpose, the Gaussian process is the best because we know that the system is kind of smooth.
I see.
Yeah.
And one more question is that, for instance, in biological data, you only have one time series. I mean, we cannot draw the limit cycle. So do you think in that case, we can use them?
Yes, yeah. Very difficult question. And
I mean, I tried a bunch of things, but I failed. Yeah.
Yeah, I cannot say anything about it. It's really difficult. So, yeah. So sorry, I have no idea, good idea. So, but like this Gaussian process requires quite small number of data, but still we need some enough data to cover the region we are interested. So if we just have a single trajectory, I'm not sure if we can do some meaningful data analysis. Yeah, I know that it's very important for biological oscillations, but I have no good idea.
Okay. Anyway, thank you very much. Yeah.
Okay, Hyopyo, go ahead.
Yeah, thank you very much for the interesting talk. So I have a couple of questions about the first one is that I was wondering for the linearly stable limit cycle problem, I saw that we have n number of eigenfunctions.
Yeah.
And I was wondering if the finiteness of those eigenfunctions or assumed or kind of implied by the problem itself.
You mean the finite?
So here, yeah. So here we have n eigenfunctions for this exponentially stable limit cycle system.
Yes.
So we have finite number of eigenfunctions in this case. So I was
principal,
wondering.
yes,
Yeah,
principal eigenfunctions. Yes.
So is this finiteness of the number of principal eigenvalues assumed or like implied by the problem itself?
Yeah, it's automatic. So it can be proven that for exponentially stable hyperbolic limit cycle, so we have the Floquet theory, we have n eigenvalues, and these n eigenvalues are exactly the principal Koopman eigenvalues for this system. And this can be shown by generalizing the Hartmann-Grobman theory for limit cycles. And
I see.
So for finite dimensional systems, I think it can be shown for kind of limit cycle with good properties like exponential stability. And because for infinite dimensional systems, I have no idea how mathematicians can prove it. We just assume it. Yeah, so in this finite dimensional case, this n is exactly the system dimension, and it can be proved.
Oh, I see. Thanks so much. And also, I have a quick question about Koopman theory for PDEs. So you showed me a reaction diffusion system.
Yes.
And I was wondering how do the principal Koopman eigenfunctions look like in this case?
We cannot draw it because it's a function of the field variable, so we cannot draw it. Yeah, but we can still calculate it in some cases. Like for limit cycles, it seems difficult, but for Varga's equation, we have an exact solution, so we can write the functional analysis.
Oh, I see. Okay.
But we cannot draw it on a plane. So yeah.
Yeah, and the last quick question is something related to the previous one. So in the autoencoder approach, you forced the latent variable obey the Koopman dynamics, this linear dynamics. So in this case, we also don't know how the closed form looks like, right? We only know the, how do I say, data combination of these latent variables Z, but we don't know how the closed form of ZT looks like exactly.
Closed form.
For example, when we define the observable, conventionally, we just put like candidate functions or something. But in this case, ZT is just a combination of several layers from the encoder part.
Yeah. So
okay.
So we lose, of course, our intuition on the meaning of the variables. They are just in a network. But
I see.
Okay, but in this system we have, okay, I think these pictures are not so nice, but this is from Branton's nice paper. This is ours. It's a bit complicated, but we introduce theta, but we cannot represent theta, so we actually introduce cosine theta and sine theta, and then several amplitude variables in a latent space, and require the neural network to obey the phase and amplitude equations for these cosine theta, sine theta, and amplitudes in such a way that they satisfy the Koopman eigenvalue equations. So yeah, maybe I'm not catching the point of your questions, but yeah, so it's like that. Then we can somehow run such latent variables in the autoencoder, although we don't know what's happening in this encoding or decoding processes. So,
Oh, all right. I see. Yeah. You did catch, and then that's the that was my question. Thank you.
okay, thank you.
And any other question, Jaehoon? Yeah, go ahead. Oh, Jaehoon, we cannot hear you. Sorry. Maybe your earphone doesn't work. Speaker. Oh, yeah. While Jaehoon fixing his problem, maybe other person can go ahead. Let's wait for him. Any other questions? Or Jaehoon, you can go another person's computer. Yes. Oh, yeah. Yes. Good.
First,
Yeah.
thank you for your impressive lecture. And is it okay?
Yes.
Yeah,
Right.
I can hear. Yes.
Yeah. I'm undergraduate student in Seoul National University in Department of Chemistry.
Good.
So, in quantum mechanics, just eigenvalues of observable operator means observable value in the system. So I'm wondering about what's the physical meaning of fluctuate exponents of Koopman operator in physical meaning?
Physical meaning of the Fourier exponents?
Yes. In the quantum oscillator?
In the quantum oscillator?
Or general oscillator?
In electronic systems?
In the general oscillator, classical. It's like how much the limit cycle attracts the trajectory. And in quantum mechanics, we can still have okay, this is I haven't shown this, but we can also consider like quantum mechanical limit cycles, and of course it's still a bit ambiguous, but at least in a semi-classical regime, we can get semi-classical description of the quantum system, where the deterministic part is limit cycle plus some noise coming from the quantum fluctuations, and then we can again do the same, exactly the same for stochastic classical oscillator. So we can get the phase equation for such a semi-classical quantum limit cycles. And I think that research are quite rapidly growing recently. And of course, in a deep quantum regime, of course, we don't know what is a limit cycle there. But for semi-classical and weakly quantum systems, we can do using very classical theory of quantum physics. We can really derive the phase and amplitude equations. That's what I think we published it in some of the papers that I cited. Yeah.
Thank you.
Maybe I'm not again. Oh, okay, it's this mathematics paper. We mentioned a bit about semi-classical and quantum limit cycle oscillator. Yeah, but the deep quantum regime is still quite unknown, so you can try. Yeah.
Thank you very much.
Nice question. And then any other question? The one. Oh yeah,
I have
go
a
ahead.
question.
Yeah. Oh yeah. Shingo, go ahead.
Thank you for the great talk. I want to ask about mathematical part of phase and amplitude reduction.
Yes.
Maybe confirm the reductive phase equation is independent on a phase equation and amplitude equation is independent.
Okay, so okay, now we are considering the lowest order perturbation in this P here, and then introduce the Koopmanian functions to derive the phase and amplitude equation. And as you see, the phase equation is independent of the amplitude equation, while the amplitude equation depends on phase through this I function here. And all other eigen amplitudes are also similar. But this is because we consider only the first order perturbation. So if we go up to the second order perturbation, then the theta and r start to mix, and we have more complicated equations. So if we don't have perturbations, they are all independent. They behave independently. And at the first order, they like this. So theta is independent of r, and r just depends on theta. But if we go up to the second order, then they mix, and we have much more complicated situation. Is this your question?
I see. And next,
Yes.
why the amplitude sensitivity function depend only on phase and
Only on
it's
phase.
independent on amplitude?
Because we are, sorry, I think I have skipped it, but we are basically considering the state in a very close vicinity of the limit cycle. So we are evaluating these gradients on the limit cycle. I'm sorry I skipped this slide quickly. But so the phase sensitivity function is the gradient of the phase function evaluated at point theta on the limit cycle. And similarly, the isostable or amplitude sensitivity function is a gradient of the Koopmanian function r evaluated on this point. So they are just the functions of phase. And the amplitude is zero on this limit cycle. So because they eventually decay. Yeah, and in general, of course, if we don't consider only the vicinity of the limit cycle, but on the whole phase space, then of course these functions depend on all r and theta. But then we are not simplifying the system, so yeah, so it's not a reduction, we just a transformation. So yeah, yeah. So sorry, I missed to clearly explain that point. Sorry. Yes.
Yeah, thank you. I understand.
And then you mean?
Sorry, is it actually similar
Same
to
question?
Shingo's question? Yeah.
Same question?
Yeah.
Okay, good. Perfect. Okay, then I think we should let Hiroya to have a lunch. Yeah, so let's thank speaker one more time. Oh, I forgot to turn off the camera record.